In the previous part of this Ralph Hurwitz, we have already discussed on how to check if the system is stable or unstable. Again, just to refresh our memory, again, if all of the numbers on the first column have the same sign, then your system is stable. If there is a sign difference, then your system is unstable. And then how many times the sign change in column one will tell you how many poles in the right hand plane. So from there, we can define if the system is stable or unstable. But how about the case when we have marginally stable system? I will discuss this in these following slides. We have a special case here. This first special case will happen if there is zero value in the first element of any row. This might cause a problem, and then you cannot solve it using the approach that we have discussed before. Why? Because when you are going to compute the subsequent row, you need to divide the negative determinant with the value on the first element of the one row above. And this, if the value of the first element on the one row above that number is zero, then you might end up into infinite number. So that's why we will have this special case. And this special case, there is a technique to solve it. The solution, the conclusion, if you have this special case, will only be either unstable system or marginally stable system. Let's take a deeper look on this special case. So again, as I mentioned, the system is never stable. It can be only either marginally or unstable system. Let's consider this second example. I have a system where the characteristic equation of the system, as you can see in this slide, s cubed plus 2s squared plus s plus 2 equal 0. In particular here, I can say that all of the coefficients have the same sign. None of the coefficient is missing. So what can we see? We cannot conclude anything, right? The necessary conditions are met, but we cannot conclude the stability of the system. So we have to form the Raoult's array. I started from S3, S2, S1, S0, as what we did before, right? And then we start to put all of the coefficients from the characteristic equation, starting from 1 from the coefficient of S cubed, 2 from S squared, and another 1 from S, and 2 from the constant. And then after that, you can start to compute this element, the B1 element. But how to compute B1? B1 is computed by taking the negative determinant of that matrix. So it's equal to 2 times 1 minus 1 times 2 divided by 2. You will end up into 0 value. So it's 0. You cannot go further. You cannot calculate this part because you have to divide 0 by 0. And it's undefined. So what do you have to do? You have to replace this 0, the value of 0 in the first element of this row, by epsilon. What is epsilon? Epsilon, we define epsilon as a positive but very small number, close to 0. But it is positive. We define it as a positive small number. So if you define this 0 as a positive small number epsilon, you can proceed with the next row. So for computing this element, you just consider this matrix. So you just consider this matrix, and then the negative determinant of this matrix will be equal to 2 times epsilon minus 2 times 0 divided by the last element on the first column, which is epsilon. So from here, since we define that epsilon is positive number, 2 times epsilon divided epsilon, then it will be equal to 2. Now you are ready to conclude the stability of the system. Look at the first column again, same like before. The first column is 1, 2, epsilon, and 2. What does it mean? We assume epsilon to be positive, so the first column, all of them are positive. There is no sign change. But in this case, the conclusion is not a stable system. For this particular case, we never have stable system. But instead, if you have all values in the first column with the same sign, the conclusion is that your system is marginally stable. No sign change on the first column, that means no poles in the right hand plane, but your system is never stable in this particular special case. So your system will have imaginary poles. Your system is marginally stable. So again, one more, I want to highlight it more. For this special case, when you have 0 on either one of the element on the first column, you will never have a stable system. The conclusion will be either marginally stable or unstable. If all of the value in the first column have the same sign, then you have marginally stable system. If there is a sign change, then you have unstable system. To show it to you, then I try to factorize the characteristic equation. So in the factorized form, the characteristic equation will be like this. From here, you can see that you will have pole at -2, but you will also have a pair of pole at plus minus j. So you have poles in the imaginary axis. That means your system is marginally stable. Let's take another example now. I have another system. The characteristic equation looks like that. S cubed minus 3s plus 2 equal to 0. The necessary condition that we discussed before are not met. Not all of the coefficient have the same sign, and one of the coefficient is missing, which is the coefficient of s squared equal to 0 there. So the system definitely will never be stable. But if you want to know whether it is marginally stable or unstable, you have still to form the Routh's array. So we do it. I started from s cubed, s2, s1, s0. I put all of the coefficient. 1 from s cubed, 0 from s squared, -3 from s, and 2 is the constant. What do we see here? We have 0 in the first column here. I cannot proceed this part. I cannot proceed the b1. I will have infinite number, right? So what do I have to do? I have to replace that 0 with a small positive number of epsilon. Again, epsilon is small but positive. That's my assumption. So I can continue to conclude the third row there. The third row will be the negative determinant of this matrix. -3 times epsilon minus 2 times 1 divided by epsilon. So that will be equal to -3 minus 2 divided by epsilon. Again, epsilon is small positive number. Don't forget with that. I complete the third row. I can move to the fourth row. I have this number. We can compute this, the negative determinant of this matrix. Matrix of 0, 2, -3 minus 2 over epsilon and 0. This will be, if you compute it, you will get 2 on the last row. But remember again here, epsilon is small positive number. So if epsilon is small positive number, 2 over epsilon will also be positive, but it will be big. You divide a number with a small positive number, so this number will be big number. You have big number here, negative 3 minus big number. What will you get? You will have negative number. So literally, this will be a negative real number, negative big number. So what will happen? If you look at the first column now, you have positive, positive, positive small number, negative big number, and positive number. So the first column, you have positive, you have negative for this one, you have positive for this one. How can you conclude? Your system is unstable. From the first column, there is a sign change. Your system is unstable. And how many times the sign change will tell you how many poles in the right hand plane. So if you look at this, you have positive and then positive. There is no sign change. And then moving to the third row, you have negative. So there is a sign change from positive to negative. Sign change once, and then moving to the last row, the sign change again from negative to positive. So the sign change twice. That means for this system, you will have unstable system with two poles in a right hand plane. If I try to factorize it using my computer, using my calculator, the factorized form of the characteristic equation will be like this. And then you can see it here. I will have one pole at negative 2. But then I also have twin positive real pole at positive 1. So as you can see here, I have two positive poles in here. My system is unstable. But beside of the special case that we have already discussed, I have another special case again here. So in the previous special case, we have 0 in the one of the element of the first column. For this second special case, this will happen if you have one row in your routes array where the components of all of the components is in one row, all of them are 0. So this is the difference between the first special case, where in the first special case only the first element on the one row that is 0, but in this second special case, all of the elements in one single row, all of them are 0. If this happens, you will have at least one pair of poles which is mirrored by the imaginary axis. So for instance, if you have this kind of special case, you might have a pair of pole that looks like this. If let's say you have one pole at negative 2, negative real pole, you will have a pair of it which is mirrored by the imaginary axis. So you will have another pole at 2, positive 2 real pole. Or you might have a pole that is on the imaginary axis like this, but there will be also the mirror of it. If you mirror this point to the imaginary axis, of course you will have the mirror at the same location again. You might also have a case where you have a complex pool in here, for instance, but of course, pools, complex pool always appear in a pair of with its conjugate. These poles, you will have another pair of pole for this special case, which is mirrored by the imaginary axis. So this will be the mirror of this. This is the mirror of this. So what does it mean? Again, for this special case, you will never have stable system because your pole, if it is negative, it is always be mirrored by the imaginary axis to the positive pole. If it is a complex conjugate pair of pole, if you have one in the left hand plane, you will have also another pair on the right hand plane because it is always mirrored by the imaginary axis. So in that two cases, you will have unstable systems. But if you have a case where the poles are in the imaginary axis, it will be mirrored by the imaginary axis. So it will fall again on the imaginary axis. So you will have marginally stable system because you have, again, pole in the imaginary axis. So same like the previous spatial case, you will never have a stable system in here. It will be either unstable or marginally stable. Now, if you have this spatial case, you need to treat it differently to solve the routes array. How to do that? We need a help from auxiliary polynomial. What is that? I will discuss it with you in the next slide. Let's consider a system with the following characteristic equation. So it's a fifth order polynomial, s power of 5 plus 2s power of 4 plus 24s cubed plus 48s squared plus minus 25s minus 50 equals 0. So definitely your system here is never stable. Why? Because it doesn't meet the necessary condition where all of the coefficient have to have the same sign. And in this case, we don't. But if you want to know whether your system is marginally stable or unstable, you still have to go through this routes array. So I will construct the routes array. I started again from the highest polynomial, S5, S4, S3, S2, S1, S0. I put all of the coefficient. 1 is coming from the coefficient of S power of 5, 2 from 2s power of 4, 24 from s cubed, and so on and so forth until the last coefficient of minus 50. Now I can continue to treat it as if it is a normal routes array. So I will compute the B1 here. How to do that? I refer to this 2 by 2 matrix. Again, negative determinant of that matrix divided by 2, the last element on the first column. Apparently, it's equal to 0. You can try it by yourself to calculate it. And then I move to the next element on this third row. I refer to this matrix. 1 minus 25, 2 minus 50, divided by negative determinants of that matrix divided by 2, the last element on the first column. When I compute it, again I get 0 here. So I have the second special case here. I have one row, the third row here, where all of the elements are 0. Of course, I cannot move further. I cannot compute the C1 here, right? So it's pretty similar like before. I cannot move further here because I have 0 in the previous row. But in this particular case, all of the elements on one row, row 3 there, all of them are 0. If you have this case, you have to treat it slightly different than the previous spatial case. How to proceed with this spatial case? In this slide, I show again the first two rows. Why do I show these first two rows? Because the next row, the row number 3, have 0 on all of the elements there. As I mentioned, if you want to proceed with this route array for this spatial case, you have to form the auxiliary polynomial. What is auxiliary polynomial? Auxiliary polynomial is the polynomial that is formed from the coefficient of the row immediately above the all zero row. So you still remember we have all zero row on the third row. All of them are 0. One row immediately above the all zero row is this row, S4 row, right? And then you need to form the auxiliary polynomial from that row, from S4 row. How to do that? Let's take a look on this. When we form the route array, you still remember this value 1 is coming from S5, 2 is coming from S4, 24 is coming from S cube, 48 is from S square, negative 25 is from S, and minus 50 is the coefficient. You don't have to bother the first row. You form the auxiliary polynomial only from this row, from the row immediately above the all zero row. So remember again, 2 is coming from what? From S4, S power of 4. 48 is coming from what? It's from S square. And negative 50 is the coefficient. So in that case, then your auxiliary polynomial will be like this. 2s power of 4 plus 48s squared minus 50. So we just form the auxiliary polynomial from that particular row only. You complete this auxiliary polynomial, and then from here we can move to the next rows. So here again in this slide, I rewrote the auxiliary polynomial that we just derived. What next? Next step, you have to take the first derivative of this polynomial with respect to s. So I will differentiate this ps with respect to s. What will I get? The first derivative of ps with respect to s will be equal to 8s cubed plus 96s. And then the next step, I will use these coefficients from the first derivative of p with respect to s to replace the all zero element, to replace these two. So the first 0, I will replace it by 8. The second 0, I will replace it by 96. Now, my third row, the elements are non-zero. I can proceed again as usual with the same approach when you are completing the routes array by taking the negative determinants divided by the plus the element on the first column. So I can calculate this part by taking this matrix. It will be negative determinant of that matrix divided by 8, and so on and so forth as usual. You can complete the routes array, and then here come the conclusion. Just look at the first column again. What do we see here? On the first column, you have positive, 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 negative. Not all of them have the same sign. And if you look at it again, the first one is positive, second is positive, 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 and then there is a sign change from S1 to S0. There is a sign change once, so the sign change once. That means you will have one pole in the right hand plane. What does it mean? That means your system is unstable. So if I refer back again to the characteristic equation and then I try to factorize it, this is the factorized form of the characteristic equation. Is as you can see here, I will have one pole at negative 1. I have one pole at positive 1, a pair of imaginary pole at plus minus 5j, and one more pole at negative 2. So as what we have discussed before, in this example, we have a pair of pole which are mirrored to each other to the imaginary axis. That means your system is unstable because you will have a pole at the right hand plane. And yes, indeed, if you look at the poles, we really have one pole in the right hand plane, which is this one. So this agrees also with our analysis in here that there is only one sign change in the first column, and then you will have one pole in the right hand plane. In addition to that, I will share you another thing here. In addition to using the Routh-Hurwitz analysis to check stability of a system, you can also use this Routh-Hurwitz technique to define the range of gain in your system that will cause instability in your system. What do I mean by that? Let's take a look on this example. So let's take a look on this unity feedback system. I have a system that, as you can see in this slide, so it's a unity feedback system where the open loop transfer function looks like this. This open loop transfer function contains one gain k there. There is one gain k here. This gain, you can tune it in your system, but now you want to know how large, how big you can increase the gain before the system goes to unstable region. You need to analyze this beforehand in order to avoid instability when you tune the gain of your controller. So imagine, let's say, I think you have ever experienced this. You are holding a microphone next to the loudspeaker. If you put the gain of your amplifier too high, you will hear a feedback noise, right? When something that is whistling very high, it at a very high tone, that is the unstable condition of your sound system. What you normally do, you lower the gain of your amplifier to get back to the stable region. So that's an illustration of tuning the gain in your system. If you put the volume gain in your sound system too high, then you will get an instability system, which is characterized by the whistling sound that you normally hear in your sound system. So you need, if you want to know what is the range of this gain in order to avoid the instability, you can do it using Raoult's array technique as well. So let's try to do it now. We have that system as you can see in the slide, and then from that system you can derive the closed loop transfer function. You know how to do this. We did it many times before. So closed loop transfer function will be equal to the forward loop transfer function divided by 1 plus open loop transfer function. In this case, of course, the open loop transfer function is equal to the forward loop transfer function. We have a unity feedback system. If you solve it, you will get this closed loop transfer function. Now we want to find the range of k to ensure the stability of the system. How to do that? First, you have to define the characteristic equation of this system. The characteristic equation is the denominator equal to 0. So once you identify the characteristic equation, then I will rewrite it here. It will be equal to s cubed plus 18 s squared plus 77s plus k equals 0. Once you have that, you can derive the Raoult's array starting from s cubed, s2, s1, s0, and then put all of the coefficient. 1 is coming from s cubed, again 18 is coming from s squared, 77 is from s, and the constant is k. Now I complete this Raoult's array in terms of k. The B1, this part, of course, this part will be equal to the negative determinant divided by the last element of the first column, which is 18. So I will get this number in terms of k. And then the last part on the last row, I will just have to refer to this array again, 18k and 1386 minus k over 18, negative determinant of that matrix divided by the last element of the first column. I will get k. So if you want to make sure that your system is stable, what does it mean? All of the elements on the first column have to have the same sign. The first element is 1, positive. The second element is 18, it's also positive. That means if you want to have a stable system, this number has to be positive and this number has to be positive as well, right? So we have these two requirements in order to ensure the stability of the system. 1386 minus k over 18 should be positive. That means 1386 should be greater than k, or k is less than 1386. That is the first requirement. The second requirement from the last row, k has to be positive. So combining these two requirements, you can conclude that if you want to have stable system, your K should be between 0 and 1386. If you set your gain K within these two limits, your system will be stable. Beyond these two limits, if K is less than 0 or K is greater than 1386, you will have unstable system. Okay, now what will happen if I set the gain K exactly at the limit of the stability? Let's choose the upper limit of the stability, which is 1386 now. So I will form the Routh array as before, but you still remember this part here is coming from. You still remember, if you refer to the previous slide, this will be equal to 1386 minus K over 18. So when I set the gain K equal to 1386, this part will be equal to 0. So this is the only element on the third row. This row only contain one element. So if you want to solve this, you can solve it either using the approach of the first special case or the second special case. I will try to solve it using the second approach, using the approach that we discussed in the second special case, using the auxiliary polynomial. So auxiliary polynomial is formed from the row immediately above the all zero row, which is this one, right? 18 is coming from the s square, and 1386 is coming from the constant. So our auxiliary polynomial PS will be equal to this. If I differentiate it once, this PS with respect to S, I will get 36S. So I will replace this 0 on the row number 3 there with 36. Then once I complete this, I can compute the last row. You know how to do this. So if after you compute it, you will get this number on the last row. What do we see now? If you look at the first column, all of them have the same sign. Positive 1, positive 18, positive 36, and positive 1386. But this is a special case, right? So you won't have a stable system. What you will have in here, because you have all elements on the first column with the same sign, what you have here, your system is marginally stable. So it's pretty logical also. At the border of the limit of stability, your system is marginally stable. When your K is less than 1386, your system is stable. When K is greater than 1386, your system is unstable. So in between, when K is exactly equal to 1386, intuitively, of course, your system will be marginally stable. And it agrees with the analysis of the Routh-Hurwitz that we just did in the previous slide. As a summary of what we have already discussed in this session, you have already learned on how to identify poles and zeros from a dynamic system, and then we have already shortly discussed on how to assess system stability. Okay, and then we see again in the next session. Thank you for your attention.